Marshall, and this is a redo because I deleted the episode 7 too quick. So we're gonna start once again.
It is brought to you by Campfire Technology. More on that later. Over the past few episodes, we've explored how our alien organisms have colonized and conquered the terrestrial realm. From humble beginnings as unassuming amphibious swamp dwellers, the chemophytes, lophostomes, and osteopods have diversified into a myriad of clades, adapting to every niche the land has yet presented them with. But in the 150 million years since they emerged from the water, their far-flung relatives in the sea will also have been diversifying. And it's about time that we revisited the ocean to see what developments have occurred since we last saw them. To begin with, the basic structure of the oceanic food webs will remain much as it has been for many millions of years. Sunlight provides energy for countless billions of microscopic phototrophs, or phytoplankton, while the atmospheric hydrogen sulfide sustains equally prolific swarms of chemotrophs, which I'll hereafter refer to as chemoplankton. All of these autotrophs will be food for tiny zooplankton like the anthostome larvae and the tachypods, and these in turn will serve as an abundant food source for larger zooplankton like the gastrozoan larvae. But the niches of pelagic nekton will remain almost exclusively occupied by the acanthopods, which first appeared almost 50 million years before the first terrestrial ecosystems, when one clade of early polypods evolved to swim by undulating their bodies from side to side, rather than using their limbs like all other clades of polypod. As briefly discussed in Part 3, the first acanthopods likely used anguilliform locomotion, where undulations pass along the entire length of the body to generate thrust, much like eels, lampreys, and some knife fish. Anguilliform swimmers tend to have elongated bodies of fairly uniform width, so that all parts of the body displace an equal amount of water. Their bodies also tend to be flattened in the direction of undulation to increase surface area and therefore give them greater leverage against the water, essentially turning the whole body into one big fin. Perhaps some basal clades of anguilliform acanthopods still survive to the present, which we'll call orthorhynchids. But anguilliform swimming is a fairly unspecialized form of locomotion, and is most efficient at slower speeds. So as the acanthopods diversify to fill the countless nectonic niches, it's likely that many clades will evolve to become faster. One way to increase swimming speed is to concentrate the lateral movements towards the posterior end of the body. Subchorangiform swimmers only use the rear 2/3 of their bodies to generate thrust, keeping the anterior third comparatively still. Because the majority of the work of displacing water is done by the tail and the hind portion of the body, the fins tend to primarily occur along these regions, while the main body is usually shorter, stiffer, and rounder than in anguilliform swimmers. Although the anguilliform swimming used by the orthorhynchids requires slightly less muscular energy to maintain, subchorangiform swimming grants greater speed, essential for escaping predators and chasing down prey. So if a clade of acanthopod were to evolve this form of swimming, they'll have a distinct advantage in competing for pelagic niches. The earliest representatives of this new clade, which we'll call hadrorhynchids, will likely take advantage of their speed to hunt small nekton. But the most plentiful source of food in the oceans are the vast swarms of plankton that teem near the surface, which one clade of hadrorhynchids may specialize to feed on exclusively, initially preying on large zooplankton like the gastrozoan larvae, before adapting to feed on smaller organisms. The setae on their feeding arms may grow into long, tightly spaced bristles to sieve tiny food particles out of the water. Having such large feathery feeding structures will increase drag and therefore make swimming less efficient, but since, by definition, plankton can't swim away, these hadrorhynchids won't need a great deal of speed or mobility to feed effectively. They can simply swim through the clouds of plankton with their feeding arms open to get all the nutrition they need. And because they have a virtually inexhaustible source of food, they'll be able to attain very large sizes, and the larger they get, the more plankton they'll be able to ingest, and over millions of years, this feedback loop may produce some of the largest species in the ocean, as has happened in many clades of pelagic filter feeders on Earth. However, somewhat similar to the situation with the lophostomes on land, the hadrorhynchids will still be limited in their maximum size by their respiration. The acanthopods breathe by extracting oxygen from the water with the gills that line their bodies. The larger their gill surface, the more oxygen they'll be able to obtain, and therefore the larger they can grow. However, the square cube law once again comes into play here, as the surface area available for gas exchange will become smaller in proportion to their body size as they grow larger, until at some point the gills will need to become impractically huge for them to get enough oxygen to maintain their size. This means that species that breathe using gills, like the hadrorachids, will have an upper limit on their maximum size, which animals like the whale shark and the extinct Leedsichthys suggest is somewhere around 15 meters or so. Despite this constraint, these giant filter-feeding hadrorachids will become the biggest animals in the oceans and monopolize the niches of large filter feeders. We'll call them tylopods. Meanwhile, another clade of hadrorachid may specialize for feeding on nekton, a lifestyle that may involve another change in their mode of swimming. Whereas subchorangiform swimming involves around 2/3 of the animal's body length, in chorangiform swimming, thrust is generated by rapidly oscillating only the posterior third of the body. This specialization in swimming style is strongly correlated with a change in body shape. The smaller the portion of the body dedicated to propulsion, the more streamlined the rest of the body becomes, favoring a fusiform or pointed oval-shaped body and a muscular tail bearing a large crescent-shaped or lunate caudal fin. This provides a further increase in speed, but comes at the cost of maneuverability. Unlike anguilliform swimmers, which can execute sharp turns by adjusting the position of their elongated bodies, chorangiform swimmers have comparatively little control over their direction of movement. To help them steer and maintain stability, chorangiform swimmers usually rely on their fins, which in the case of our hadrorachids may evolve from the limbs that line their bodies, which have long since lost their role in propulsion. When moving through a medium like water or air, an animal needs to remain stable along 3 axes of rotation. Firstly, the animal needs to control roll, or side-to-side teetering, which can be achieved by evolving fins that stick out perpendicular to the body. If positioned towards the front or back of the body, these fins also help maintain pitch, or rotating forwards and backwards. Finally, a yaw, or turning left and right, can be adjusted with dorsal or ventral fins, which typically occur posterior to the animal's center of gravity. Additionally, the 4 feeding arms common to all acanthopods will present unnecessary drag and decrease their speed and swimming efficiency. So to make them more hydrodynamically optimal, this clade may evolve to keep their feeding arms pressed together into a streamlined cone. You'll probably notice that with all of these constraints taken into account, we've ended up with a body shape quite similar to that of many fish species on Earth. Because of the hydrodynamic pressures exerted by a medium as dense as water, the basic fish shape that we're familiar with on Earth is likely to be common in pelagic nekton on Earth-like planets throughout the universe. On Earth alone, it's independently evolved in cetaceans, marine reptiles, and even sea slugs. Another adaptation strongly correlated with a pelagic lifestyle is countershading, where the ventral side of the body is more lightly colored than the dorsal side, meaning that when viewed from below, they blend in with the light coming from the water's surface, and when viewed from above, they're camouflaged against the darkness of the deeper layers of the water column. This color pattern benefits both predators and prey, and so is likely to be widespread among many oceanic clades, including among our clade of chorangiform swimmers, which along with their speed and streamlined bodies will help them to become the dominant clade of pelagic predators. We'll call this clade the teleopterids. From here, different clades of teleopterids may specialize for feeding on different types of prey, which is likely to involve modifications to their mouth parts. Another pressure imposed by the density of water is that, when a predator lunges at a prey item, the resulting turbulence may push the prey out of the predator's reach. Aquatic animals on Earth have evolved a variety of different feeding mechanisms to minimize this risk. Some, like groupers and bass, use suction feeding to draw the prey and the surrounding water into the mouth, while others, like the slingjaw wrasse, goblin sharks, and dragonfly larvae, have extendable jaws that can dart forward to grab prey without producing appreciable turbulence. If a clade of teleopterids specializes for feeding on small nekton, they may converge on the latter solution. The middle pair of feeding arms may become streamlined harpoons to dart forward and impale prey, with their setae evolving into sharp, backward-angled spines, while the lateral arms may broaden into robust, tooth-riddled appendages to restrain and butcher prey once it's caught and to pass it into the mouth. This sophisticated armament will equip these hadrorachids to feed efficiently on small nekton, and will earn their clade the appropriate name Dorapods. Another clade of teleopterids may specialize for hunting larger prey, which may entail yet another change in their form of swimming. The final and fastest variation of body-driven swimming is thunniform swimming, wherein virtually all the propulsive force is provided by the tail fin, seen in many large predatory species like tuna, barracuda, and some sharks. This form of swimming is also correlated with an elongated, torpedo-like body that allows for rapid acceleration, which will give these teleopterids a substantial edge in competing for the niches of macropredators. Most of the prey species that form these teleopterids' diets are large enough to not be significantly affected by turbulence, so evolving a hydrodynamically optimal feeding mechanism isn't as much as a priority for these macropredators as it is for smaller species like the Dorapods. Instead, the setae lining their feeding arms may evolve into rows of serrated teeth to deliver powerful bites and to rip chunks of flesh from their prey. These teleopterids may gain supremacy over the pelagic ecosystem soon after they first appear, and by the time they've established themselves as top predators, they may be large enough to rival the filter-feeding tylopods in size. We'll dub them temnopods. Faced with the competition from all these new clades, the orthorhynchids may not fare as well, as their anguilliform design doesn't grant them the necessary speed to compete for the niches of active predators in the open ocean, and so many of the pelagic orthorhynchids may be driven to extinction. But some species may still find niches in environments like the shallows along the coasts. In many such places, the marine snow and abundant plankton may cultivate huge reefs of sessile anthostomes, providing a habitat for a unique assemblage of organisms. In some ways, the differences between the reefs and the open ocean is analogous to the differences between the forests and the steppe. In the open sea, where there's virtually no form of cover or shelter, it pays to be optimized for speed, but the complex landscape of the reefs favors specializations for maneuverability. In this regard, the orthorhynchids have an advantage, as their anguilliform swimming allows them to change direction more rapidly than other forms of body-driven swimming. Many species may retain a long, slender body shape to help squeeze through confined spaces among the stands of anthostomes, but other species may further optimize for maneuverability with yet another change to their manner of swimming. All of the methods of swimming we've discussed so far involve the body and the caudal fin in the production of thrust, but an alternative commonly found in many reef-dwelling fish is to instead achieve propulsion by beating the fins back and forth, keeping the body and tail comparatively motionless. This is called median paired fin swimming, and is generally slower than any of the various forms of body-driven swimming, but the chief benefit that it provides is a much more precise control of movement, which is essential when it comes to navigating the complex terrain of the reefs. Although most acanthopod clades have lost the use of their fins for propulsion and have instead invested in body-driven swimming, some of the reef-dwelling orthorhynchids may re-evolve the limb-driven swimming of the ancestral polypod, developing the fins lining their bodies into 7 pairs of broad paddles. Many species of reef-dwelling fish also exhibit a laterally compressed body and enlarged dorsal and ventral fins, giving them a much greater control over their turning, which the orthorhynchids may emulate by evolving thin, leaf-shaped bodies with tall fins running along their dorsal surface. Another likely result of adapting to life in the reefs is a change in coloration. In contrast to the countershading frequently seen in pelagic swimmers, reef-dwelling animals often have coloration that helps them blend in with the surrounding terrain, so most orthorhynchids may have color patterns to camouflage them against the sediment and the calcareous turrets of the anthostome colonies. While the basal clade of orthorhynchids, which we'll call tenipterids, will rely on the cover of the anthostomes to keep them safe, these more derived forms, which we'll call remipterids, will use their agility to evade predators. It's worth noting that each of the modes of swimming we've discussed here are likely to evolve independently in many of these clades, just as how on Earth many unrelated groups of fish have converged on similar swimming methods to suit similar lifestyles. The straightforward linear progression I've presented here is fairly simplified for the sake of clarity, and in practice, any given clade won't be restricted to only one form of swimming. The reefs will offer the orthorhynchids protection from larger predators like the temnopods, but they'll have to share these environments with other creatures. One clade very likely to find a home amongst the reefs are the marine tentaclostomes, relatives of the forms that gave rise to the lophostomes. To distinguish them from their terrestrial cousins, I'll refer to the marine forms as lithostracans. Like the ancestral tentaclostomes, these lithostracans aren't very well adapted for swimming, and so can't compete for predatory niches in the open ocean, instead mainly thriving in benthic environments on the seabed. Species in more open habitats may protect themselves from predators by retracting their limbs into their calcareous shell.
Wait, up to 10 million pesos! Sali na! Sige gawin niya! Ubus na!
But in the reefs, they may gain more protection from hiding among the stands of sessile anthostomes. In this case, having a large, inflexible shell may become a handicap, as it will prevent them from squeezing through narrow spaces. So much like the malacoforms and the coleostracans on land, some of these reef-dwelling tentaclostomes may lose their shell to give them more flexibility, and to let them access tighter, more secure hiding places. These spaces may also serve as ideal spots for launching ambushes, which they'll rely on for catching prey much faster than themselves. We'll give these shellless creatures the fitting name anostracans. Another likely resident of the reefs will be the marine sarcopods, which, once again, to distinguish from their terrestrial relatives, will give the name coelopods. Much like the lithostracans, these creatures don't have any overt adaptations for swimming, but instead avoid predators by burrowing beneath the sand. The setae lining their limbs are embedded in vibration-sensitive cells or mechanoreceptors to detect movement in the surrounding water, alerting them to incoming danger. The majority of coelopod species are benthic detritivores, feeding on the marine snow and the other organic matter among the sediment. But some species may expand into the many other niches offered by the reefs, possibly even evolving predatory feeding habits. These species may increase the number and sensitivity of the mechanoreceptors along their cephalothorax, with the anterior setae elongating into antenna-like structures, while the mouth parts may adapt for grasping and masticating prey. Lying in wait within their burrows, they may use their sensitive mechanoreceptors to detect vibrations in the water above them. When prey passes overhead, they'll erupt from under the sediment and dispatch it with the tooth-like setae on their oral tentacles. But specializing for the niches of ambush predators may put these coelopods in competition with the anostracans, which may mean that the two clades won't exist in the same ecosystems, or that they'll specialize for hunting different species of prey. We'll call these predatory coelopods trichopods. Many of these marine clades may also have representatives in freshwater habitats.
Get
The
it
various
correct,
lineages of
all
acanthopods are likely to
pods.
have independently colonized the inland rivers and marshes, and we'll cover their diversity in more detail in future episodes. But some freshwater inhabitants of particular note are the native tentaclostomes. These species, descended from the same amphibious clades as the terrestrial lophostomes, may retain their ancestors' amphibiousness, able to come out onto the land for short periods, but still needing to return to the water to breed and to stave off desiccation. While most marine tentaclostomes are benthic predators, the line that led to the amphibious clades descended from more generalist species that supplemented their diet by feeding on the early chemophytes. This being the case, many of the freshwater and amphibious species that survive to the present day may be omnivorous, or perhaps even herbivorous. They may graze on the low vegetation along riverbeds and mudbanks, using their long eye stalks to look above the waterline. To distinguish them from their fully terrestrial and marine counterparts, we'll call them mysostomes. The sarcopods may have some surviving amphibious representatives as well. These forms trace their ancestry to swamp-dwelling scavengers, and so their diets may tend more towards carnivory. Notably, they will have diverged from the osteopods before the evolution of internal skeletons, so they won't have any bones and thus won't be able to support themselves on land very effectively. Also, because air is about 800 times less dense than water, vibrations don't propagate through it as appreciably, so their mechanoreceptors won't function nearly as well when on land. On top of that, with the proliferation of the osteopods, the amphibious forms may have trouble competing for terrestrial niches, so all of these factors may consign most species to a life spent predominantly in the water. Many may feed on the mysostomes, using their powerful, robust mouthparts to crack open their shells. Once again, these species will constitute their own clade, distinct from the fully terrestrial osteopods and the marine coleopods, and so to differentiate them, we'll call them metaxopods. All of these aquatic clades will flourish over the 120 million years following the invasion of land by the chemophytes, lophostomes, and osteopods, but the steadily changing atmosphere and the subsequent shift in climate will have far-reaching implications for the pelagic ecosystems. The drop in temperatures following the decrease in atmospheric carbon dioxide levels will disrupt the ocean currents, depriving many areas of the sea of oxygen and nutrients, and the diminishing hydrogen sulfide levels will make chemosynthesis less efficient, and so the once abundant chemoplankton may experience a substantial decline in their diversity. Some clades may even be forced to invest in other forms of nutrition, evolving saprotrophic or even fully heterotrophic lifestyles, ensnaring and ingesting other plankton with long ciliated feeding structures. This revolution among the plankton may result in the collapse and restructuring of many of the pelagic ecosystems. In many areas, plankton may not occur in large enough quantities to support the filter feeders, and without them, many of the predatory acanthopods that feed on them may be driven to extinction. It will take several million years for the acanthopods to reclaim their former diversity after the climate stabilizes, but as they do, they may face competition from some rather unexpected adversaries. As well as affecting the oceans, the climate change event will concurrently reshape the terrestrial ecosystems, changing the dominant landscape from lush forests to open steppe. In the last episode, we discussed how some of the osteopods and lophostomes adapted to this new environment, but not all the terrestrial clades will have representatives on the plains. Some groups may not be adaptable enough to compete for niches on the steppe, instead remaining within the surviving regions of forest. Some of these areas, particularly around the equatorial coasts, may still receive enough rainfall to form large swamps and marshes, and these sorts of environments may prompt some of the terrestrial inhabitants to expand into aquatic niches. On Earth, many species that descend from fully terrestrial ancestors have secondarily adapted for life in the water. These sorts of animals are sometimes described as amphibious, but this label can be a bit problematic because it's also used to describe actual amphibians. Alternatively, these animals are also often described as semi-aquatic, which is also somewhat problematic as it's quite difficult to rigorously define and encompasses a very broad spectrum of lifestyles, ranging from animals like water voles, which occasionally enter the water to feed on aquatic vegetation, to animals like seals, which spend virtually their entire lives in the water, only coming onto land to breed and to evade predators. On our alien planet, the first step in the transition to a semi-aquatic lifestyle may occur when some of the wetland-dwelling clades undergo adaptations to help them wade or swim across the waterways that pervade their habitat. Some of the most prolific forest dwellers are the adaptable platodonts, most of which spend their lives among the branches of dense foliage. But in the wetlands, stands of trees may be separated by stretches of shallow water, which the platodonts will need to cross periodically to reach new feeding areas. Their elongated limbs, primarily adapted for climbing trees, will make them awkward swimmers, but as they evolve to spend more time at ground level, their legs may become shorter and broader to more effectively serve a paddling lifestyle. And once they evolve to swim effectively, they may expand their diet to include the many food sources that the water offers, like the mysostomes, metaxopods, and freshwater acanthopods. To specialize for preying upon these clades, the platodonts may evolve a more streamlined body shape and the ability to hold their breath for several minutes at a time. As adaptable generalists, comfortable both on land and in the water, these platodonts may be a common sight around many wetland areas across the supercontinent, living in a similar way to otters, muskrats, and platypuses on Earth. Let's call them copitarsons. Along with small generalists like these, semi-aquatic adaptations are also occasionally seen in megafaunal herbivores, like hippos, capybaras, and the extinct desmostylians, so some of the analogous herbivores on our alien planet may see similar developments. While the line leading to the titanopods may thrive on the steppe, some of the more basal clades of megalobrachids may remain within the equatorial jungles, where they'll need to adapt to a climate of high rainfall and regular flooding. Like the copitarsons, these megalobrachids may begin their semi-aquatic transition by adapting to traverse areas of shallow water, which will have the added benefit of granting them access to the aquatic vegetation that grows along the riverbeds. At present, no other large animal feeds on these plants, and so the lack of competition may encourage these megalobrachids to specialize for the niches of large semi-aquatic herbivores. Their elongated pedipalps, once used for reaching upward for food among tree branches, may now be repurposed for reaching downward to forage for underwater vegetation. Their spiracles and sensory organs may migrate towards their dorsal surface, allowing them to breathe and see above the waterline while the bulk of the body is submerged. Although not quite as big or specious as their steppe-dwelling cousins, this radiation of megalobrachids, which I'll name prenobrachids, will still constitute some of the largest megafauna within the swamps and marshes. And with such an abundance of prey in the water, some predators may be incentivized to adopt a semi-aquatic lifestyle as well. On the open plains, the Deinignathans may get outcompeted for predatory niches due to their bulky, inflexible bodies not giving them the speed to chase down fast prey. But they'll still survive within the remaining pockets of woodland, using the cover of the ample vegetation to ambush large prey. In this regard, any areas around lasting sources of fresh water will form ideal hunting grounds, as prey will routinely come to these areas to drink. One early radiation of Deinignathans may evolve to live in these areas exclusively, possibly co-evolving with the prenobrachids, which may serve as their principal source of prey. At this point, they'll live in much the same way as crocodiles, and as such, they may converge on similar adaptations. On Earth, the crocodilian body plan has independently evolved many times among completely unrelated clades, suggesting that it's an optimal design for semi-aquatic ambush predators. One of its signature characteristics are the long yet robust jaws, which are streamlined for efficient swimming and capable of delivering incredibly powerful bites to restrain prey and drag it backwards into the water. The osteopods have a fairly different jaw structure to vertebrates, but the Deinignathans' enormous mandibles are already well suited for seizing large prey, making them somewhat pre-adapted to the niches of semi-aquatic ambush predators. Like the prenobrachids, their eyes may move towards the top of the cephalothorax to let them sense prey above the waterline, and their spiracles may be repositioned on the upper abdomen to let them keep the majority of the body hidden beneath the water. This line of Deinignathans, which I'll call Odontognathans, may rapidly achieve widespread dominance of the freshwater habitats following their first appearance, after which they may diversify into a number of more specialized forms. Most of the early Odontognathan species will be macropredators, feeding primarily on terrestrial prey and other semi-aquatic animals like the prenobrachids. We'll call these forms Trachognathans. But as the group diversifies, some species may avoid competition with their larger relatives by specializing to feed predominantly on the freshwater acanthopods. On Earth, animals with equivalent feeding behaviors are called piscivores, but once again, we run into a bit of terminological trouble here, as strictly speaking, this term is used to describe animals that feed specifically on fish, and there are obviously no fish on this alien planet. So for the sake of exactitude, I'll coin the term acanthivore to describe their lifestyle. Just like the predatory teleopterids, these acanthivorous Odontognathans will need to find a hydrodynamically optimal way of feeding. Because it's a lot harder to get a grip on prey when in water, semi-aquatic piscivores often have noticeably different mouth parts and dentition to their terrestrial relatives, frequently involving elongated jaws with interlocking pointed teeth, and sometimes additional sharp protuberances lining the inside of the mouth. Likewise, these Odontognathans may forego their ancestors' robust jaws and broad serrated teeth, instead evolving narrow, slender mandibles with prominent needle-like teeth. Since most of the job of catching prey is done by the elongated mandibles, the pedipalps may shrink to reduce water resistance, though they may still be used to masticate prey once it's caught and to pass it into the mouth. To let them move more effectively in water, they'll need to evolve an efficient means of swimming. But unlike crocodiles, the Odontognathan's inflexible limb girdles, common to all synischians, may make body-driven swimming difficult to evolve, so it may be more likely for them to adopt a style of swimming similar to the median paired fin swimming seen in the remipterids, propelling themselves with back-and-forth strokes of their powerful limbs. To prevent their airways from flooding when they dive underwater in pursuit of prey, they may evolve specialized muscles to let them constrict their spiracles, similar to the palatal valve seen in crocodiles or seals' ability to open and close their nostrils. This clade of odontognathans, which we'll call dolichognathans, will be smaller than the macropredatory trachognathans, but will still be capable and prolific predators of the acanthopods they share the water with. And because they no longer feed on terrestrial megafauna, they won't necessarily need to stay within close proximity to the land, so some species may expand their feeding areas into the coastal shallows. Initially, they'll be prevented from exploiting pelagic niches by the temnopods, which have been the dominant oceanic predators for over 70 million years. But when the climate changes and the marine ecosystems are thrown into chaos, many of the top-level niches will be left vacant, which may provide an opportunity for the coastal dolichognathans to colonize deeper waters. Despite their semi-aquatic disposition, the freshwater odontognathans will still need limbs suited for terrestrial locomotion, as the variable environments of the wetlands may occasionally demand that they emerge from the water. But the coastal species won't need to come onto land nearly as often, and so can afford to adapt more completely for an aquatic lifestyle. Their limbs may become powerful flippers, making them slow and cumbersome on the land, but greatly increasing their speed and maneuverability in the water. In this style of limb-driven swimming, roll, pitch, and yaw can be controlled by adjusting the position of the flippers, so stabilizing fins aren't as important as they are in body-driven swimming. To reduce drag, their pedipalps may reduce even further, possibly being held flat against the mandibles to form a sort of streamlined beak, very similar to the conical mouthparts of the teleopterids. However, these coastal forms, which we'll call pelagotheres, will be held back from becoming fully aquatic by their one and only tie to the land. Being osteopods, their developing young are contained within a leathery ootheca, which must be laid out of water or else oxygen won't be able to diffuse through the membrane to reach the embryos. This means the pelagotheres must be forced to drag themselves ashore to breed, and thus they need to retain some ability, however limited, to move around on land. But this constraint can be circumvented with one major development. If the female is able to retain the ootheca within her body until the young are developed enough to hatch, they can be birthed directly into the water, and thus the mother will be freed of the need to make landfall. This form of live birth is subtly different from the kind seen in mammals, because the young aren't connected to the mother via a placenta or an equivalent organ, and the mother provides no additional nourishment to the young during their development. Instead, is more akin to the method of reproduction seen in some species of snakes, sharks, and amphibians, where the eggs are simply withheld by the female until they hatch internally. This mode of reproduction is sometimes referred to as ovoviviparity, and we'll go into it in much more detail in a future episode. The pelagotheres that evolve this innovation will now be able to completely forego any capacity for terrestrial locomotion and evolve for a life spent entirely in the water. One immediate advantage that this provides is an increase in potential body size. On land, an animal can only get so large before it collapses under its own weight, but in the water, the effects of gravity are counteracted by buoyancy, and therefore aquatic animals can reach much larger sizes than terrestrial ones. The egg-laying pelagotheres, which we'll hereafter call actotheres, are restricted to sizes at which they can still support themselves when they come ashore. But with the advent of live birth, the fully aquatic pelagotheres will be able to reach sizes so large that if they ever did find themselves on land, they'd be crushed under the weight of their own bodies. This increase in size will be complemented by their efficient respiration. As already mentioned, the acanthopods have an upper limit on their size imposed by their gill surface and the levels of dissolved oxygen in the water. But the pelagotheres' mechanism of active air breathing lets them take in much more oxygen than would be possible with the acanthopods' gills, letting them fuel body sizes even greater than the tylopods and temnopods. These pelagotheres, which I'll call thalattotheres, will be the first clade to evolve a fully aquatic lifestyle from a terrestrial origin, and are destined to become the new masters of the ocean. From here, the thalattotheres may diverge into two lineages. Some species may evolve to feed on large amounts of small prey, eventually adapting to feed on the clouds of plankton, with their needle-like teeth evolving into a comb-like sieve to strain the water. And with such an abundance of food, they'll become gigantic and whale-like, replacing the tylopods as the top-level filter feeders. These forms may maintain flippers of roughly equal size, which provides a balance of speed and maneuverability, somewhat reminiscent of the bygone plesiosaurs on Earth. Based on this limb configuration, we'll call them isopterygians. A separate clade of thalatothere may maintain a diet of large nekton, evolving into fast, powerful macropredators. These species may adapt for speed, generating the majority of thrust by flapping their second pair of flippers like wings. The frontmost flippers may help control and stabilize the enormous cephalothorax, while the hind two pairs of flippers may serve as rudders to aid in steering, making their style of swimming more similar to that of seals, sea turtles, and penguins. To contrast them with their filter-feeding cousins, we'll call them anisopterygians. Faced with these new competitors, many of the larger canthopod species may be ousted from the megafaunal niches they've held for millions of years, but they still maintain the advantage of not needing to return to the surface to breathe, and so can survive at depths that are inaccessible to the thalathotheres. The sheer enormity of the oceans offers such a diversity of habitats, each one varying in temperature, salinity, oxygen, light, and numerous other factors, that it's difficult to speak of it as a single biome. But for our purposes, what we've outlined here will serve as an adequate picture of how the aquatic ecosystems have developed over the last 150 million years or so up to the present day. But while all of these developments are taking place, new environments are opening up across the supercontinent, some of which will demand unique survival strategies from potential colonists. In the next episode, we'll return to the terrestrial realm to see how our alien life forms evolve in response to extremes of heat and cold. Thanks to
So bye guys, see you in the next episode. See ya!